is all about safe systems of work, and do your people really understand them? And how can we get to a place perhaps where they have a better understanding? That is today's session. Just very briefly, a little bit more about me so you know where I'm coming from. My name is Ian Pemberton. I'm managing director of a company called Human Focus, but my main interest from your perspective is I'm a chartered ergonomist, and my area of specialism for the last sort of 35 years is very much around cognitive ergonomics. So looking at how we can support people in the workplace to make better decisions, to not only avoid human error, but to develop positive capacities. So very much around this space of safe systems of work. How do we build in safe systems of work? So what I'm going to be doing with you this afternoon is sharing, firstly, some of the science. What do we understand is required to achieve this holy grail, shall we say, of health and safety? And then I'm going to get practical. I'm going to share some case study materials from some of my own work to try and illustrate, to make the science real for you. Okay, so there we go. The contents of today's session is, first of all, what is a safe system of work? I'm asking that question because on my travels, there's often a lot of misunderstanding about what a safe system of work is. So we'll take a brief look at that. We'll look at the critical components of a safe system of work. And then I will dive into, let's have a look at how you actually implement one of these in practice. And this is where I'll introduce some of the case study material. And by effective, what I mean by effective is, firstly, your people can understand what you're giving them. They're able to apply it. And thirdly, it actually helps to keep them safe. That's what I mean by effective. And I hope by the end of today's session, we will have had a tick in all three of those boxes. And if we can do that, then perhaps that will give you some useful insights that you might be able to apply in your area. So let's begin. What is a safe system of work? Apologies for those of you outside of the UK, but here is one definition, which is a pretty decent one. HSE define it as a number of elements, and not surprisingly, it's on the plan, do, act, and check. So planning, make sure you've got all your tasks listed, you know what they are. You then get necessary organization in place, get the necessary resources, training, all that sort of stuff. Then you've got to go out and do it and control how the work is actually happening. And then you've got to be able to improve as you go along. So no surprises there. A couple of key things you've got to have: trained personnel. So a safe system of work is more than a bit of documentation. It's about having people out there who actually know how to do it, and you've got to check the effectiveness. So this is how I apply that and other similar guidance, 4-step, to make this real for you. The first step is really all about, you've got to document what you know, you've got to capture the operational knowledge, and I'll show you how we do that later. And then in simple terms, you're going to then go and deploy this stuff out in the field. It's no good, particularly the supporting training and documentation, if it's sitting in a file, in a filing cabinet. Literally, I've seen that. Or indeed the electronic version on SharePoint that nobody knows where it is. And even if they do, they don't use it. You've got to support the performance of work as done. And you've got to make sure that it's happening day to day in the way you imagine it's happening. And then you've got to be looking for improvements, because this stuff that we create is always, well, it conforms to the second law of thermodynamics. It's constantly drifting to increased entropy. It is disorder, basically. So it's always degrading, and you've got to always looking to adjust and improve, and that will then complete the circle. So there we are. That's planning, organization, and monitoring and reviewing. So let's have a brief look, a little bit more detail into this. So a big issue with documentation is quality control. where is this documentation? What's the quality of it? How do you know that it's what you expect it to be? How does it conform to your standards? Once you deploy, we've said you've got to have of people that are trained. So you've got to have a training system, and you've got to have a way of getting this out into the field. It's got to be at the moment of doing, not just in the classroom. So we'll be looking at smart forms and other latest tech that enables to do this. As we're performing, it's simple things like, who are you? What training have you got? And what tasks are you performing? And does this match and marry up? And in more complex, high-risk task areas, you may have hundreds of safe systems of work, perhaps thousands of employees, people moving around. You've got to manage that process. So if you put all this time and effort into developing your safe systems of work, you've got to be able to check that the right person is doing the right task at the right moment. You've got to be able to monitor who's actually using this stuff. If there's nobody using it, it's a big red flag. And then we've got to have this update monitoring. So that's what we mean by a safe system of work. And by the way, therefore, that means a heck of a lot more than just a standard operating procedure or a method statement or whatever else you want to call it. Those elements are really important and they are foundational elements, but a safe system of work is an awful lot more than that. So let's go and have a look a bit more at the critical elements of a safe system of work. Well, to kick off, some of the science that underpins this stuff is 50-odd years old now, going back to the Second World War. This is a B-52 American bomber, Second World War. When it was built, it was the world's first four-engine plane. Just bear with me 1 second. I want to grab my mobile phone so I can keep a track on time. Check I'm on time. Okay, we're doing good. So yeah, this was the world's first four-engine plane, and at the time it was the most complicated, probably, machine aircraft that had been produced, and they were crashing, and they were crashing largely due to pilot error, because there were so many controls that had to be absolutely in the right place, and if you didn't get that right, you were going to crash. So Boeing, the manufacturer, were scratching their heads, and at the time they thought, oh, this is so complicated that perhaps these machines are too difficult to fly. And then they had a brainwave. They came up with this. It was the world's first safety checklist. And there you go. That's I said B-52 earlier, sorry, B-17. So the B-17 takeoff and landing checklist. And now checklists are just, have absolutely become an ingrained part of aviation safety to this day. And indeed, they've made a massive difference to safety, and checklists are now being applied in many other sectors: healthcare, energy, nuclear. This guy here, Atul Gawande, a surgeon, has applied it into the healthcare sector, where there are many surgical errors from highly experienced, highly trained surgical teams, but it's the so-called automatic skill-based errors. And Gawande's done a lot of research for the World Health Organization, put these into hospitals around the world. Very simple things like checking numbers of counts of surgical items at the beginning and the end of procedures to check they haven't left items inside patients. And it's made a massive difference to performance. Surgical errors. So surgical errors have fallen by a massive 70% with these checklists being introduced. And things like IV line infections by 66%. So a checklist effectively is an operating procedure that's embedded into the task. These procedures, these processes, so-called human performance tools, can make a massive difference to human performance. We know that, the science is there. The difficulty is that they have what are called bounded applicability. So checklists are good, but they're good only for a certain part of the task. So if you look at this video, this is literally Top Gun, and the question I have for you is, how do you proceduralize that? How do you write a checklist for that? once these pilots go up into the air and they're dogfighting, it's completely dynamic, it's completely unpredictable, and a lot of work that goes on out there is exactly like this. It's not predictable. You can't write a checklist for it. And in fact, this chap here, a leading researcher in so-called naturalistic decision making, which is the study of how people make decisions in the real world. This chap here called Gary Klein, he's been instrumental in founding this area and has done a lot of the foundational scientific research in this space, which really kicked off in the 1980s, was funded by American military, American emergency services. And this really was the first insight. And Gary Klein tells the story literally of going to Miramar, the Top Gun school that became famous from the movie. And he's walking past two combat pilots who were scratching their heads. And he said, "What's the matter, guys?" And he said, "Well, we've got to write an operating procedure for our fighter pilots." And he said, "Well, what's the problem?" He says, "Well, we don't know how to tell them about dogfighting." And that's when he became intrigued. So we also need, in addition to procedures and checklists, we need a lot more to deal with this unpredictability. And this is another part of safe systems of work. So what this means is, here is an actual, another checklist system within the aviation sector. This is for takeoff and landing. All good. And again, this is necessary, but if you look at a couple of components here, if an abnormality exists, the captain decides and initiates a rejected takeoff. Well, how does the captain make that decision? And, on what basis is the decision being taken? What's he looking for? What are the signals? How do you know when you've got to make a rejected takeoff? Here's another one. They will recognize unstable flight path condition and be prepared to execute immediate recovery. What is an unstable flight path? How do you know to what extent does the flight path have to become unstable in order to execute a recovery? There are many, many things that are really, really important to safety that are not in procedures and processes that are making your task today safe, but are not in these procedures. So in other words, these procedures are not flying for dummies. They're not following these processes by rote. They're intelligently interpreting them. And there's something more above this that has to also form part of a safe system of work. So what is that other thing? Well, it's called expertise. It's called what we call, from a psychological point of view, tacit knowledge. And tacit knowledge is invisible. It is in people's heads. It is automatic. If you ask an expert what they do, they will find it very difficult to tell you. So here you go. Here's the nature of expertise. The first time that most people see this picture, what they're looking at is a random set of pictures, and they're saying, well, what is that? If I now show you this picture, the picture on the left immediately makes sense, because you now have in your head effectively what we call a mental model. It is, or in other words, a pattern. And you're able to match that apparently random information to that pattern and make sense of it. And once you've got that mental model, if I show you other versions of that picture, you'll instantly know, you'll instantly see the B. So this is what we call cognitive diamonds. And a cognitive diamond is a mental model, and this is how Gary Klein and others have found that experts are able to make really good decisions in the real world. They are doing what's called recognition prime decision making. So they are matching this mass of information that's coming, and they are matching it to patterns that they've got in their heads. And experts literally are able to see things that are invisible to everybody else. It's only through this pattern matching that they can see things in the real world. So that's a cognitive diamond. This is a cognitive diamond in action. So this is Garry Kasparov, the chess grandmaster. He's playing simultaneously 30 other grandmasters, chess masters, and he beat all of them. And look how fast he's making his decision. almost instantaneously or within about a second. And this is very much the nature of skilled expertise. It's very fast, it's completely automatic. And what Garry Kasparov is doing is he's matching each of these chessboards to literally millions of patterns in his head that he's built up over time. And in simple terms, he's got more patterns in his head than the chess masters that he's playing, and therefore he's able to figure out and make the best move very quickly. So this is the nature of expertise, and we need this expertise on top of procedures and other guidance in order to achieve truly safe systems of work. So one way of thinking about this is there are different kinds of systems in the real world, and a safe system of work will have multiple systems as part of it to achieve safe outcomes. So this is a useful way of thinking about it. This is what's called the Cynefin framework, and Cynefin has 4 quadrants. So we've got clear, complicated, complex, and chaotic. And again, in simple terms, Cynefin says on the right-hand side, we have what are called linear bounded systems. And a linear system typically is a piece of technology, piece of equipment, and it's predictable. If you push a button on a machine, certain things will happen. And if it breaks down, you can get an engineer in and they will be able to fix it. It's predictable, it's modelable, it's controllable in that sense. So it's linear and it's bounded in the sense that we can put limits on it. On the left-hand side, we have what are called linear unbounded systems. So non-linear means that small changes in one place can have a big change somewhere else, and you get lots of feedback loops. So it's not linear from A to B to C, but C can lead to A, and B can lead to A, and A can lead to C, and so on. So you've got a lot of interactions. It's unbounded in the sense that it's very difficult to say where the system starts and finishes. So the really simple message is over on the right, this is stuff that we can predict ahead of time, and therefore it's good to do that and try and control it. And the stuff on the left is unpredictable. It's all the stuff that we cannot predict ahead of time. And so if you think of it in terms of that dogfight, predictable linear stuff is that the aircraft and takeoff and landing, you know, to start the engine, to get up into the air. There's only one way to start an engine on an airplane. And if you don't push the buttons in a set way, you are not going to start the engine. And we saw this with the B-17. If you don't set the flaps, get the undercarriage down, you're going to crash. And there's only one way to do that. So this is linear, it's bounded. And again, Atul Gawande with his checklist, he was very much working on this right-hand side. Non-linear, unbounded is very much about the dogfight in the air. It's unpredictable, and yet it is real life. And so when we go over to the left into complexity, we need to enable our people in different ways, and checklists and procedures are not going to do that. In fact, if you apply checklists and procedures over on the left-hand side, you're going to make it worse, not better. So let's see what this means in practice. So down in clear, a clear system is a simple bit of kit. It's a single pathway through. You don't really need any expertise to do it, to use a clear system. So using a coffee machine to get a cup of coffee, press button, put your cup in, you get yourself a cup of coffee. That's an example of a linear, clear, linear bounded system. And here we're going to apply rigid controls. You have to do it in this sequence. And if you don't press that button in this way, you're going to get into trouble. So this is very much the space of standard operating procedures, checklists, and other such controls, rigid controls. If we move up into the complicated space, so we still have kit, we still have linear systems, but here you need technical expertise to make the decisions, because there will be multiple pathways. And in fact, you will probably have multiple systems coming together, and you need people to make good choices, and you need to, in what's called, be able to see the big picture, to see that this bit here relates to that bit there, and therefore I need to configure that to fit here. But it's still a linear bounded system. So here we have what are called governing controls. So we're giving people, yes, we're giving them operating procedures, but we're also giving them leeway as to where and when those procedures apply, how they apply, and we're giving them latitude to make decisions within that space. So that's what's called the governing control. And as we move over into complex, here this is unpredictable, and we need here, we have what are called guiding controls. So people have got to make sense of what they're seeing, so sense making, and then they've got to make decisions based on what they're seeing. So here we have what are called guiding controls, and this is where people have the most space, and they need that space, and they need the expertise in order to fulfill the design of your safe system of work. And it's the gap between all the written stuff, all the documentation, and what goes on in the real world. So non-technical, this area of complexity is very much the space of what are called non-technical safety skills, or NOTS. And NOTS were first sort of identified as being a big safety issue in the 1970s, when there were a lot of aviation crashes. Tenerife air crash is the most famous. NASA got involved. And essentially, there was nothing wrong with the planes. There was nothing wrong with the kit. It was all to do with the way the air crews and air traffic controls were communicating and working with each other. And this was very much about how do we give people the cognitive diamonds they need to make better decisions at the moment of doing. And as a result of Tenerife, there were 6 main areas of non-technical skills: communication, leadership, decision-making, situational awareness, teamwork, fatigue, and stress management. So these are got nothing to do with flying a plane. They've got everything to do with how we communicate with each other, how I lead at that team, how we make decisions as a team, and so on. So these were termed non-technical skills. And then as a result of that research, it's become ingrained in aviation and other sectors too. If we go into oil and gas, for example, if we go back to Piper Alpha, 1988, the Cullen inquiry found that fundamentally what triggered that disaster was a failure in communication, leadership, and decision-making. It had nothing to do as such with the pipe work and all the technical stuff. It was all of these non-technical elements. And if we come forwards to Deepwater Horizon in 2010, exactly the same things going on: communication, teamwork, and decision-making. So we know that these non-technical skills are fundamental to helping teams deal with complexity, the messiness of day-to-day work. And it's these non-technical skills that help them to make better decisions in the face of daily pressures and unpredictable situations. So there you go. The science is well established in this area. It's evolving. This is one of the leading researchers in the space, Professor Rona Flynn. She's based at Aberdeen University. Rona has done a lot of the foundational research in the space, written numerous books, if you want to learn more. So what this tells us is that within a safe system of work, you're going to have different types of documents that fulfill different roles to achieve this desired outcome of a truly safe system of work. So down below, you're going to have a bunch of miscellaneous documents, standards, policies, all of that stuff. Then you're going to have your procedural stuff, operating procedures, method statements, that kind of documentation, really, really important. And then we're going to have task guidance. So this is very much around, this is how you put these procedures into action. So this is very much about what you have to do, but this stuff is very much about how do you do it. So there's the what and the how. And at the very top, you may well be familiar with these 3 elements, but at the very top is what is known as decision requirements and heuristics. So decision requirements is all about how do you deal with complexity. And we know from the work of Gary Klein and others that in complex situations, the guiding controls that we will give people are called mental or cognitive heuristics. So the military are very big into this now. So an example of some simple military heuristics would be, if you're out in the field, keep moving, take the high ground, stay in touch. And those three heuristics, guiding heuristics, have been proven to be very effective at devolving and empowering frontline teams, but still getting intelligent, adaptive group behavior. So in order to develop heuristics for any task, you need what are called the decision requirements. So in this scenario, what are the decisions that have to be taken, and how can we support them with relevant and effective heuristics? And I'll show you how you can do that and how you can build that. I'll give you an insight. So if we think back to Cynefin, the three main areas we're operating in is clear, complicated, the linear stuff, and then complex, the non-linear, the unbounded. So your procedures, all of that stuff, very much the space of clear. Procedures and task guidance, very much the space of complicated. And all three of those together, very much the space of complex. And the message is, it's not either or, it's all together simultaneously in one integrated system. And that is when you start to get a truly safe system of work. So just very briefly, this provides step-by-step guidance. This provides the technical guidance for applying procedures. And this provides what we call the tacit expert knowledge for decision-making in complex adaptive situations. So in other words, it's about taking all those patterns of bees and building them into people's heads, just so that we get that kind of behavior that we saw Garry Kasparov. Garry Kasparov was not following any standard operating procedure. He was pattern matching in a complex adaptive situation. And that's what we need in complexity. So there you go. So you may be familiar with this. This might be new. And this is very much the space of so-called cognitive systems engineering, or CSE. And that is the background I come from. And cognitive systems engineering is really about this top bit. How do we do this? How do we get the expertise out of people's heads? And how do we build systems to literally make people smarter? So what I want to do now to sort of finish this off is to make this real for you in a case study. Let's apply it to an actual industrial task and see how these different elements all come together and how it actually can be used to build a safe system of work. So what I want you to imagine is we're looking at a task. It's an industrial task. The details are not that important, but it gives us a framework to discuss this. So I want you to imagine we've got a couple of guys and they're working on a large industrial process. They're about 4.5 meters up in the air on some scaffolding. There's a huge bit of tank work with a pipe going up to a hopper above, and they're working on a bit of pipe work here. And these two guys are maintenance engineers. And let's suppose that this task is that they've been tasked with replacing a joint on a bit of pipe work that is dripping, and they need to fix the leak. So here they are up the scaffolding, and they've got all that material up there. One guy is holding the pipe work, the other mechanical fitter engineer, shall we say, and he starts to try and undo the nut, and the whole joint starts to spin on the pipe work. And indeed, the pipe work was just dripping, and now a lot of other fluid starts to come out. So they get a bit concerned and they think, well, we need to get out of here because this is a lot of hot, very high pressure liquid. And as they're getting out of the way, the joint actually moves and it breaks, and a lot of very hot pressurized liquid comes out, and one of the guys gets badly burnt. And because there's so much liquid coming out, they have to jump down just to get out of the way because there's no proper space up there. And this is actually an accident happened, and we know this has happened. And so the first message is you can use this kind of learning from previous accidents and incidents to inform your safe systems work. How do we improve a system like this? So now let us apply our framework, and let's go through this and look at what might be involved in building a safe system of work for this task that we've just reviewed. So if we come back to Cynefin, we said that we've got essentially 3 element areas we're working in. And by the way, chaotic is a complex system that becomes unordered, and that's when accidents happen. So you don't want to fall into chaos. So we're actually working in the real world in clear, complicated, and complex. So let's go through those 3 areas and look at what needs to be in place in each of these 3 areas. And it's very different in each of the 3. So we've said that clear. So the task was to go and fix a leak on a joint underneath this big bit of industrial kit. And there's a picture of the actual joint that they were actually working on. And so we will have an operating procedure here that says, this is a joint, this is how you replace a joint, and there's only kind of one way to do that, and that's a very appropriate thing to have a checklist of equipment, of steps that you will go through in order to replace that joint. That is an appropriate thing to have, and indeed we need it, because if you don't do it in this set of steps, then you're going to get into trouble. But as we've already said, there's a lot more than just a set of recipe steps. So one of the things we can start to do is to use this cognitive systems engineering approach is a technique called cognitive task analysis. And we can start to unpack from experts' heads. So when you are actually replacing a joint like that, what are you looking for? What are the warning signs and the things that are telling you whether the job's going well and whether you need to change approach? And through a cognitive task analysis, what we found, or what I found, this was an actual case study, the general workforce were looking at things like this: the amount of rust, the fact that that was a non-return valve, which was important for reasons that I won't go into now, and the amount of force that they were having to apply on the nut, and that told them whether it was tight or whether they were just coming to the point of stripping the thread. So most people in that factory, those, if you like, are the cognitive diamonds they had in their head about that task. But we went and then spoke to and did interviews, cognitive task analysis interviews with top experts, and this was what they had in their head, a lot more than, in fact, the guys that were actually involved. They were looking at things like the color of the sealant tape, because if it was really yellow, it told them the age of the joint. They were looking at where the leak was, because where the leak is makes a very big difference. Again, I won't go into the detail, but the location of the leak, if it's this side of the joint as opposed to that side of the joint, it's 2 very different jobs. They were looking down on the floor for drip marks on the floor, and those drip marks told them, for example, how long this leak had been occurring. And again, the length of the problem makes a massive difference. The fact that the valve started to spin was a massive red flag. They were also looking at things like spanner marks on the joint, and these, if there were marks, again, it told them how often this joint had been worked on. So in other words, the experts had a much richer set of mental models about this task. None of this was documented. None of this was there. And this is the difference between what you do and how you do it. If you think of it in terms of a cooking metaphor, your operating procedure is the recipe. This stuff is the chef. And what you need in these high-risk situations are chefs, not just recipe followers. The recipe is important, but the recipe alone does not get you a really great meal at the end of it. So you can unpack these cognitive diamonds very quickly from the heads of your experts, and you can build very rapidly very simple bits of training to get these cognitive diamonds out of the heads of your experts and into the rest of the workforce very quickly. And literally in this instance, the training was this photograph and a bit of explanation of these cognitive diamonds. So that's what the experts were seeing. That's what the average worker was seeing. So even with a procedure, we need to be looking for the cognitive diamonds. So there we are down in clear. If we move up into the complicated space, now the picture starts to get more complicated. And by that, we mean there isn't just the joint, there is a bigger picture here. There is a process within which this joint fits. And if you're going to work safely on the joint, you need knowledge of the wider process. So this is a schematic of the process. This is the vessel that was above them, and this vessel had a lot of liquid, high pressure, high temperature, and the joint they were working on was down here. Now, there was a system of work to isolate this whole process, to turn off all the valves, to make sure that this bit down here was isolated and that nothing was going to come out. And in fact, that whole process had been isolated. All the valves had been switched off, they'd been locked out and so on. But this process has basically, the vessel has a lot of humidity within it. And over a course of about an hour, this humid air condenses and very hot liquid forms in the base of the vessel, over 100 litres. Even though then the system is isolated, you've still got a lot of very hot, high pressure liquid in the bottom. And you'd only know that if you had the tacit knowledge about the bigger picture. And what we found in this, so this is this knowledge of the process within which this valve fits, is another cognitive diamond, and it forms very much part of the complicated space. And what we found was in this particular accident that the guys working on that joint, they knew quite a bit about the joint, and they knew quite a lot about how to replace the joint, but they had virtually no knowledge about the process within which it fitted. So top experts would have immediately have known, working on that task, that although it has been isolated, in order to work safely now on that particular joint, which is down here underneath this vessel, which has probably got all of this condensed, very high pressure, temperature liquid, we just need to open what's called a relief valve, which just drains the vessel to check there's nothing in there. And they always would check that. Again, none of this was documented. It wasn't part of the procedural documentation, but it was in the heads. And there's just huge amounts of these types of cognitive diamonds. So they were caught out in this instance, partly because of lack of cognitive diamonds about the joint, but also lack of cognitive diamonds about the whole bigger picture. So that starts to show us the complicated space. Now, if we come over into complex, this is very much the space of teamwork. And in this instance, there were two engineers working on the joint. There was a shift supervisor. The supervisor was tasking these individuals with doing the work. And there were a whole bunch of team dynamics. And this then got into feelings of psychological safety, ability to say, do you know what, I'm not sure we should be working on this task, on this shift. It was a night shift. I'm not sure I've got enough process knowledge to deal with the bigger picture. And also, as the job unfolded during the course of the shift, there were signals about what we started with this job is now it's creeped, and the mission has creeped into something else. Do you think maybe we should pause at this point? Do you think maybe we should reassess whether this is a good idea to carry on or not? All of these things are in the complex space. And this also, all of these factors also played a critical role in this accident. So this is very much the space of non-technical skills. This has got nothing to do necessarily about replacing a joint. It's got everything to do with how we interact, as we've said, as a team. So when we come back to this this framework, let's have a look at some examples of these different elements, particularly decision requirements and heuristics. So in this particular safe system of work, a cognitive systems engineering approach with cognitive task analysis, there were actually 7 key decisions, or what are called difficult decisions. And difficult decisions are defined as a decision that a less experienced person is likely to get wrong. So in this instance, there was assessing whether it was reasonably safe to go ahead with this job on this shift, negotiating a delay or change if it was not safe to go on this shift, establishing a safe system of work for the job, assessing whether the equipment was all properly isolated, assessing whether there was any residual energy in the line that was about to be broken into, that whole thing about flicking the relief valve, all of that stuff, assessing whether there was a change, whether a change of approach or stopping the job once it had started was necessary, and selecting how to change that approach or stop the job if indeed it was necessary to do so. So if we apply our technical, non-technical framework to this, we can see that that is technical, that is non-technical, that is technical, that is technical, that is technical, and these 2 at the bottom are non-technical. So you can see that difficult decisions can be a mix of both technical and non-technical, and you need all of them. And there will be cognitive diamonds in all of these decisions, both technical and non-technical. So what you do then in terms of decision heuristics is the first thing you do is build from a CSE point of view of what are called decision requirement tables. And you can unpack from your experts, okay, that's a difficult decision. How do we actually, on what basis are you making that decision? What are you looking for? And in simple terms, it's the pictures of the bees. They're looking for patterns in the environment. And they're saying, well, if that is there in that way, I do this. If this is in there and that, I do this. And these patterns can be extracted from their heads. And this is how you codify it. So this was decision 1, assessing if it's reasonably safe. So this column says what makes this decision difficult. These are the expert cues or patterns. These are the things they're looking for. These are strategies that they use to apply that. And this is a comparison between your experts and less experienced. This is how they're likely to make these decisions in different ways. So from these, what are called DRTs or decision requirement tables, you can then quite easily build heuristics. You can also build simple simulation training that trains this type of decision requirement heuristics out to your people quickly. So these are all cognitive diamonds. Think of it that way. So here's a very quick clip of a simple, you can do this online and offline. This was an offline example. So the training is what's called simulation training. You actually put people into a scenario and go, okay, what would you do here? And these scenarios can be very simple. They could be pictures, they could be short animations, but this is what they look like.
We'd like you to imagine that you are working on a night shift. You're about to perform a maintenance task, and you receive the following pre-job briefing. Listen to this conversation carefully. We will then ask you some questions at the end of it.
We've got to carry out a repair to pan 13. There's a leaking union on screwed pipework that injects steam into the bottom of the pan. This is a medium priority job, but I want it fixing this shift, please. Process will decide when it's the...
So you get the idea, and the key point here is that the end of this is not multiple choice, it's not drag and drop, it's free text entry or just talking. So it's open, it's what's called a formative assessment. And they are asked questions like, what information would you be asking of the supervisor? And on this basis of, if we give you this information, what would be your assessment of that task? And if you then had to, if you decided that you are not going to go ahead with that task on that shift, what would you say to that supervisor? How would you say it? Give us the actual words. And as I say, they can either say it out loud or they can type it in. And then that technology is using artificial intelligence then to assess their answers. And the AI has got all the cognitive diamonds from the decision requirement table. So it is literally as though one of the organization's top experts are there, and they giving coaching feedback. So what is the evidence around this approach? These are what are called decision-making exercises, or DMXs. And DMXs are these little simulation training. This is how you build the mental patterns, the heuristics. And we did a little study here. We ran 3 DMXs, and the 3 DMXs were ran without any training. Then we gave the individuals a little bit of information to build their mental models, and then we reran the DMXs. And the whole thing was each one of these was about 1 hour of training, so about 3 hours in total training across these 3 critical decisions. And this is what we found. We found before the DMX, this was the average score across the cohort, and these people had an average tenure of about 10 years. So these were not rookies. So in other words, they had about a quarter of the tacit knowledge, the cognitive diamonds, as opposed to the top experts in that organization. And these top experts had at least 30 years of experience. After 3 hours of training, we'd more than doubled their tacit knowledge, their decision-making heuristics. But there, as you can see, there was still only about 3/4 of the level to the top experts. But it shows you that you can capture these heuristics, you can train them out very quickly, and you can accelerate expertise development from literally decades to hours. And that's what this is not me saying that, the science, there's good science to show that. Now, would you take this approach on every single safe system of work in your organization? If you're thinking, oh, this sounds like a lot of work to me, absolutely not. You've got to take a risk-based approach. So here's from one client, we would go into a site, help them write, show us all your safe systems of work. And on this one particular site, they had 366. And then we go through a risk ranking. And what we find usually is the number of high-risk tasks are quite small. So high-risk tasks are going to be those that are potentially going to kill people, or serious, like life-changing injury, or blow the plant up, have massive environmental or commercial implications. So you really want to take a different approach depending on the level of risk. And I will go into some of these techniques in a minute, but basically with low risk, I mean, you could park those immediately, start with your high risk. You will have a much more comprehensive approach to your high risk safe systems of work, and you can work back and take subsequently lighter touches depending on the level of risk. So let's have a look at a few solutions from my previous work. Quality control on documentation. That's a quote from the HSE. They're basically saying, just because you've got a bit of paperwork in a document doesn't mean you've got a safe system of work. You do need to know what's going on in the field. So you do need a system that can track and monitor usage. And by that, I mean not just the training of your people, but how are your people interacting with your documentation? How are they using it? How are they applying it? And you need to be able to track and monitor that. And there are online systems available to do that in a fully integrated way. So we talked about and documented it. I don't have enough time today, but very briefly, there are a whole bunch of cognitive systems engineering techniques available for doing this. One of them is called walkthrough talkthroughs. You can use dynamic videoing, where the dedicated apps designed to do this, so that you're kind of edited by the time you finish it. So it's very quick, but you're basically talking through in a very precise way. There's a methodology to it. And this is what some of the videos actually look like.
Okay, so we're going to clean up the adjusted rods first. So it's going to give a bit of spray.
So you get the idea. But in addition to that, you can run what are called these cognitive task analysis interviews. So what you've just seen there is the what. These are the steps. but you can also run CTA interviews with experts to then unpack the cognitive diamond. So this is a brief little snippet of a CTA with one resident expert. So this is what they sound like.
First thing is where they're putting the hands on the spanners. Right. So if you grab hold of a spanner, you'll see my hand. If you put your hand on there, push down. If that spanner slips off, it's underneath. Yeah.
Sometimes you can smell a bit of residue. So using your sense of smell as well to smell whether the belts have got hot. You can smell, it's like a strange rubbery carbony smell that you can smell. That smell means that the belt's probably been slipping.
So you get the idea. These cognitive diamonds then can be built in, certainly in the complex, complicated, and we can train these out. So that's the how. We need that very much. And then in terms of documentation, there are a whole bunch of cognitive usability design things I've thrown up here. These are just examples from some of our clients. And if this is what your standard operating procedures look like, then this is well below best practice. These are poorly formatted, poorly written, very difficult for people to follow. So this is a set of guidelines, human factors guidelines that we've developed to help our clients format these. This is the content of it. It gives the guidance on the layout of these documents, using color strategically, making it a lot easier and clearer, but also in terms of how you write it. So it's also the visual as well as the written. So, you know, don't do it this way, do it that way, using present tense, writing in short sentences, using positive commands versus negative commands. All of these things are clearly in the research show that these things makes it a heck of a lot easier for people to read, scan read, and access the documentation. And literally, there are hundreds of these elements in the written thing, in the graphical thing. This is the realm of a very experienced technical writer, human factors specialist. And it used to be a massive job to apply this, particularly if you've got hundreds of these or even thousands of these documents. The great news now is that this can be automated, and we're using proprietary AI tools that have got these are cognitive diamonds within each page. So these cognitive diamonds are now in AI tools. You can feed in your document, and it will automatically rewrite it, reformat it in literally a minute or so. So you can go, you know, from this is an example of the AI bot. You can go from like 95 words to 67 words. So it shortens it and it rewrites it, puts it into bullets, as well as visually reformatting it. It can also write test questions. It can develop training, simulation training. So a lot of this stuff can now be fully automated. Thinking about putting it out in terms of smart forms, you can also now start to place this documentation not just in training, but they can become intelligent forms as part of work documentation. So you can use QR codes. These can be scanned off documents, off machines, and you can give people access to this. It can be video, it can be checklists, it can be checklists and video. And this is an example of one.
Slacken off the V belts until they.
So this is a way of embedding your documentation out into the workplace to give people immediate access at the moment of doing. This is another example. These are inspection tasks. So you can put bits of QR codes on bits of equipment, gives them immediate access to the form, the guidance that enables them to do the inspection. They can load reports from it. So you can embed this stuff into smart forms, smart apps as people are actually working. As people are performing, we've said that you've got to check that the right people are doing the job on the right day. They've got the training. So you've got to give line managers out in the field the ability to say, well, who are you? What's your training? And you've got the necessary SSOW training for that task. So this is a electronic training passport system. So all the records up there on the learning management system are accessible out into the field. This can be put onto documentation. So these QR codes are for individuals. This is their personal training passport, if you like. If you scan any one of these passports, you can then get access to that individual's training records. So alignment, we've got examples of clients who are running industrial processes, production lines, and they've got people moving up and down the line. They can very quickly see what training they've got, and these QR codes can also be put on, many clients are putting them on trainee badges. That's another way for line managers to access this stuff in the field. So this is all about competency assessment in the field. And then finally, we want people, as they're doing the work, to saying, you know, I did this task today and there was a problem. This documentation didn't marry up to what I was dealing with, or I spotted something new. And this information needs to be being fed back to you and then fed back into the safe system of work. So again, you can use this technology to enable people on the people at the point of harm to actually be able to easily report back on any given task. That's the key. So, for example, that could form a simple after-action review. We use the different, difficult, dangerous, the 3 Ds. So was there anything different today? Was there anything different, difficult, or dangerous? And they can provide text feedback. They can put video clips on there. They can assign it to individuals. And if there are any actions that need to be taken to improve the safe system of work, that can be tracked and monitored on the same system. So this is a fully integrated system that in fact goes back to that portal that you saw right at the beginning. So you can see on one portal whether your safe systems of work are being used, interacted with, and in fact being updated on a regular basis. Really important. So if you've got safe systems of work that are not used, or no problem, that definitely is a problem. Okay, so there we are. We're coming to the end now. I hope that has been helpful to you. I hope you can hopefully see that will all help your people to understand, apply, and help them to keep them safe. So thank you very much. Final thing is that is a research paper that I've written, Crystallizing Cognitive Diamonds in a Sugar Factory, how CTA can be used to improve learning from serious accidents. So that paper documents, that's been presented at a couple of conferences, but that research paper documents this whole approach and the science behind it, the evidence that supports it, and a little bit of information about how you do it. So if anybody would like a copy of that paper, more than happy to email that to you. That's my email address there, ian@humanfocus.co.uk. So now I'll shut up, and I'd be more than happy if anybody has any to answer any questions that may be there now.